Shor's algorithm, phase estimation, and a whole family of powerful quantum algorithms each solve totally different problems. But pop the hood on any of these, and you'll find the same subroutine running underneath, the quantum Fourier transform. In this episode of Qiskit in the Classroom, we'll break down how it works. In 1822, while studying how heat flows through materials, the mathematician Joseph Fourier made a bold claim. Any function, no matter how complicated, could be expressed as a sum of sines and cosines. Today, this kind of decomposition, called the Fourier transform, is an essential result used daily in pretty much all fields of science and technology. Even some of our own senses rely on similar principles. When we hear a chord on a piano, our brain is subconsciously breaking the complex sound waveform into its constituent tones, each corresponding to a sine wave of a particular frequency. But, as I mentioned, the Fourier transform was discovered over 200 years ago. It's old news. What I want to focus on today is its application in quantum computing, the quantum Fourier transform. The quantum Fourier transform was developed in the 1990s, and it remains a foundational tool in many quantum algorithms, including phase estimation, amplitude estimation, and Shor's factoring algorithm. Today, we'll take a deep dive into the quantum Fourier transform, or QFT for short. First, I'll review the classical Fourier transform. Then we'll explore how the QFT is implemented on a quantum computer. Finally, we'll look at one of its applications, the phase estimation algorithm. By the end, you'll have the foundation you need to understand our next video in the series, which focuses on Shor's algorithm. I'm going to use my son's toy piano here and play a C. This Python code will record the note and output a waveform. And here it is. If we apply a Fourier transform to this data, we'll convert it from a plot in the time basis, where we see the oscillations in time, to the frequency basis. There's one clear peak at about 260 Hz, meaning the original time basis waveform was just a single frequency tone. I only played one note, so that makes sense. And as expected, 260 Hz is a middle C. What if multiple notes are played at once? Then the waveform becomes more complicated. But the frequency spectrum clearly identifies three peaks. These are the three notes in a C major chord. What's happening here is called a discrete Fourier transform. We discretize the signal into n time bins, giving us a vector of data points x0 through xn-1. The discrete Fourier transform picks out which frequencies are present in that signal by multiplying it by periodic functions with different candidate frequencies, then summing over all the time bins. When that frequency is present in the signal, the two oscillate in sync and add constructively, and you get a large output. When it isn't, the contributions are sometimes positive, sometimes negative, and wash out to zero. The periodic function we use is e to the I phi, which equals cosine of phi plus I sine of phi. Packaging the sine and cosine into one in such a way keeps the algebra clean. You can think of this function as oscillating in two perpendicular directions in the complex plane simultaneously. The cosine part oscillates along the real axis, and the sine part oscillates along the imaginary axis. When you put them together, they make spirals in the complex plane as you move along the time axis. Putting this together, the discrete Fourier transform looks like this. Y sub k equals 1 over square root of n times the sum over j from 0 to n-1, x sub j times e to the I 2 pi j k over n. where each y sub k represents how much of the frequency k was present in the original signal. Together, they form the frequency domain vector y sub 0 to y sub n minus 1, which would be like our spectrum here, where again, the frequencies are discretized. Now that we have some background on the discrete Fourier transform, let's apply it to the quantum case. The QFT looks almost identical to the classical discrete Fourier transform. It's phi sub y equals 1 over root n times the sum over x from 0 to n minus 1 e to the I 2 pi y x over n times x. The only difference here is that our vectors x and y are replaced with quantum state vectors, x and phi sub y. X is the state written in the standard basis called the computational basis, which is just the set of classically allowed states where each qubit is either 0 or 1. Phi sub y is a Fourier basis state. Another key difference between this QFT and the classical version is that the complex amplitudes are now an essential feature of the equation, rather than a mathematical convenience. Now, what do these Fourier basis states look like? All of the Fourier basis states are equal superpositions of all of the computational basis states, but each differs from the others in the rate at which the component's phase winds around the complex plane. To understand this more concretely, let's take a look at the 4 Fourier basis states of a 2-qubit system. Here, the blue bars show the amplitude of each component, computational basis states 0, 1, 2, and 3, which represent the 2-qubit states 0, 0, 0, 1, 1, 0, and 1, 1. These bars can point in any direction in the complex plane, which shows what phase that particular component has. The lowest Fourier basis state is the one whose phase is constant across all computational basis states. The next Fourier basis state is the one whose components' phases wind from 0 to 2 pi just once as you step through the computational basis states. The next basis state winds from 0 to 2 pi twice. Finally, the highest Fourier basis state is the one with the fastest varying phase, winding from 0 to 2 pi 3 times. In general, for an m-qubit system, there will be 2 to the m Fourier basis states, whose phase winding frequency ranges from constant up to 2 to the m minus 1 windings. So when we take the QFT of a quantum state, we're doing the same basic analysis that we did for the musical waveform earlier, determining the Fourier frequency components that contribute to the quantum state of interest. Now let's use Qiskit to Fourier transform a state. We'll prepare some state in the computational basis, then apply a Fourier transform and measure to see what that state looks like in the Fourier basis. Keep in mind that when we measure, we only see the magnitude of each component, not the phase, so our measurement won't capture all of the information. Let's try transforming a single computational basis state. We'll start with making a random computational state with this circuit, which looks like this when we measure it in the computational basis. Now let's Fourier transform the state with QFT gate here. And here's the histogram. The populations of each state are more or less equal, give or take some experimental and statistical noise. So, if you take the QFT of a single computational basis state, the result is an equal superposition of all states. If you're familiar with Fourier transforms, this probably doesn't surprise you. One basic principle that can help us build an intuitive connection between a function and its Fourier transform is that the width of a function is inversely proportional to the width of its Fourier transform. So something that is very localized in time, like a very short pulse, will require a broad range of frequencies to generate that pulse. That signal will be broad in Fourier space. This fact is actually related to quantum uncertainty. Heisenberg's uncertainty principle tells us that there's an upper limit on how well you can simultaneously know a particle's position and momentum. So if the uncertainty in x is small, then the uncertainty in momentum must be big, and vice versa. Make sure you visit the module to see more Fourier transforms. The best way to build intuition for this is to play around with the code yourself. So far, we've just been applying QFT gate, taking it as a given that it accomplishes the Fourier transform that we want. But how is it actually implemented on a gate level? Let's start small with a single qubit, so 2 basis states. QFT2 transforms the computational basis state 0 and 1 into Fourier basis states phi sub 0 and phi sub 1. You might already recognize the gate that accomplishes this. It's the Hadamard gate. So h times 0 equals phi sub 0, and h times 1 equals phi sub 1. The Hadamard is spreading out the input state into a uniform superposition. Equal amplitude on every basis state. That's the first requirement of any QFT output. Every Fourier basis state has the same amplitude on every term. It just so happens that the Hadamard also gives us the correct phases of the states for the 1 qubit case. For larger dimensions, though, simple Hadamards won't suffice. Let's bring back the 2 qubit or 4 basis state example. QFT4 should transform the 4 computational basis states like this. So Hadamards will help generate these states by spreading out each computational basis state into a uniform superposition, but for more control of the individual phases, we need something called a controlled phase gate. The controlled phase gate takes a control qubit and a target qubit and applies a phase e to the I alpha to the target qubit's 1 component, but only when the control qubit is in the state 1. The last gate we need is the swap gate, which exchanges the states of the 2 qubits. This one is almost pure bookkeeping. It just makes sure every phase is in its proper place. So the circuit that implements the QFT4 will look like this. We have our Hadamards, our controlled phase, and the swap gates. And in general, the procedure for building a larger QFT circuit on m qubits is iterative, like a Russian nesting doll, where each layer adds a factor of 2 in dimension, with the smallest doll at the center being QFT2, the Hadamard gate. To wrap one doll inside the next, you apply a Hadamard to the top qubit, along with a series of phase and swap gates to get you the correct phases on each qubit state. Here are a couple more QFT circuits. QFT8 and QFT16. Okay, now that we've seen what a QFT is and how to implement it, let's apply it as a subroutine in quantum phase estimation, QPE. QPE is itself a subroutine in many larger algorithms, including Shor's factoring algorithm, which we'll see next time. The goal of QPE is to estimate the eigenvalues of a unitary operator. If you're familiar with linear algebra, you'll probably remember that an eigenstate of an operator U is a state that leaves U structurally unchanged. Applying U just multiplies it by a scalar, the eigenvalue. So U times psi equals lambda psi if psi is an eigenstate. Eigenstates and eigenvalues are ubiquitous in quantum computing. An eigenvalue might represent the energy of a Hamiltonian in a simulation or encode information about the prime factors of a number in Shor's algorithm. Because of this, QPE is a really important subroutine. So what does this have to do with QFT? Any eigenvalue lambda of a unitary operator has a magnitude of 1. So we can write it as lambda equals e to the 2 pi I theta, where theta is a real number from 0 to 1. That's the same periodic complex exponential that forms the Fourier basis states, which already suggests the QFT will come into play. Let's see exactly where. Here's a diagram of an example QPE circuit. The bottom qubits are prepared in psi, which is an eigenstate of U. The top qubits are the control qubits, which will encode an approximation of theta. The more control qubits, the better the approximation. We first put them in a superposition with Hadamard gates. Next comes a series of controlled U gates, U, U squared, U to the fourth, and so on, where U to the K simply means U applied K times in succession. Each gate applies its unitary to psi only if the corresponding control qubit is in 1 and does nothing otherwise. Now, since psi is an eigenstate of U, applying U doesn't change its structure. It only picks up a phase factor, e to the 2 pi I theta. So applying U to the K picks up e to the 2 pi I theta times K. Now here's the weird part. Although the unitaries are being applied to these bottom qubits and the top qubits are only being used as controls, it is the state of these top qubits that actually changes. This is the phase kickback mechanism, which I've covered in previous videos. It's like rowing a boat. Your paddle pushes the water backward, but the net effect is to move you forward. Each control qubit picks up a different power of the phase e to the 2 pi I theta. After all the controlled unitaries are applied, the full state is... Look familiar? The control register has the form of a QFT. So, if we apply the inverse QFT, we'll convert the phase information of the control qubits into amplitudes, which we can then read out and use to approximate theta. The quantum Fourier transform is more than a mathematical curiosity. It's the mechanism that lets quantum computers turn hidden patterns in the quantum phase into useful information. We saw how it mirrors the classical Fourier transform as a change of basis, how it's built from Hadamards, controlled phase operations, and swap gates, and how it's an essential tool for quantum phase estimation. The quantum Fourier transform enables quantum algorithms to uncover structure that classical methods struggle to access, from energy levels in quantum systems to the number theoretic patterns behind factoring. If you want to explore the QFT yourself and see how it applies to quantum phase estimation, head over to the module on the IBM Quantum Platform linked in the description. See you next time.